All right, so I think I want to do this problem 40. I'm in 15-2. I just found this problem 40, which says this. Oh, yeah, anyway, it's got some directions somewhere. Find the work done by the force field on a particle moving along the given path. They asked me to do this. Find the work done by the force field on a particle moving along a path. So they're asking for that, so I know I need to do that. Now what do? They give me a vector field. The vector field they give me is 3D. So this can be done in 3D or 2D. The vector field they give me is YZ, XZ, XY. YZ, XZ, XY. All right, so that's cool. I need a vector field. The other thing I need is the path. They should give me a curve. They give me a path. Now they describe it. Sometimes they give me pictures. Sometimes they just describe it. What do they do? Okay, here they say it's the line from 0, 0, 0 to 5, 3, 2. It's a line from 0, 0, 0 to 5, 3, 2. And then they actually do have a little picture of this one up above, but the picture doesn't help too much. I'm going from 0, 0, 0 to the point 5, 3, 2. I don't know, that's not 5, 3, 2, that's not in the best proportion in a way there, but from 0, 0, 0 to 5, 3, 2, I'm going on this little line out here into the first octave here. You guys okay? All right, so what I taught you the other day was that in order to do these, we come up with the parametric equations for the path. We need, the paths need to be written in terms of t. In fact, the whole damn integral gets done in terms of t. The vector field is dot producted with dr, but this whole thing is kind of done in t's with the parameter t. So that's all dictated by the path. So what do I got here? I got a line in 3D. It goes from the point 0, 0, 0 to the point 5, 3, 2. Do you remember how to write parametric equations of a line? Maybe not, but it was chapter 11, and it was real easy. What did we need? We needed parametric equations of a line. I used to write it like this. And what I needed was a point on the line. I would put a point here. You know what? I think I'll pick 0, 0, 0 as my point. And then what I needed was a parallel vector. Well, if my line goes from 0, 0, 0 to 5, 3, 2, I think a good parallel vector would be the vector that goes from 0, 0, 0 to 5, 3, 2, which would be the vector 5, 3, 2. And so so that would be 5t, 3t, and 2t. I'm trying to remind you of the good old, what we call parametric equations of a line, which look like this. From chapter 11, parametric equations of a line look like that. The x naught, z naught, y naught, z naught was a point on the line. The ABC was a vector parallel to my line. And this was a pretty easy one. From 0, 0, 0 to 5, 3, 2, that's the equation of my line. Now, I can talk parametrically like this, a set of parametric equations. But sometimes, the other way to talk is with vector-valued functions. And again, I explained this in the previous lecture. So another way to talk, instead of a set of parametric equations, is to write this as a vector-valued function, which would be the x, the y, and the z components of the vector. So that's... And what I'll do is I'll get sloppy here in the future, and I'll call this a parametric equation rather than a vector-valued function, probably. I mean, to me, they're the same thing. I mean, there is subtle differences here, but they're the same thing. So cool, I found my path. What do I do then? I want to set up this integral. Oh, by the way, you know what I really need? How much t do I need to go from 0, 0, 0 to 5, 3, 2? I mean, we set up this parametric equations, we wrote it as a vector-valued function, but how much t do I need to get from where I'm starting to where I'm ending? 5t. How much t do I need? In other words, t starts at what number to what number, which, by the way, those will be the bounds on my integral, because I'm going to be integrating with respect to t when this is all set up here. I think t should start at 0 and go to 1.
Oh, because it's a unit vector.
Well, no. I think it should go from 0 to 1 because that'll make me start here and end here. With the parametric equations that I set up, 0 to 1 will make me start there and end there. A 0 will give me 0, 0, 0. A 1 will give me 5, 3, 2. I want t to go from 0 to 1.
Oh, I see.
Okay, I needed that. What else do I need? Okay, I need my dr. You know, my dr is just the derivative of r. So I need this derivative. It's called dr. It's just the derivative with respect to t. It's 5, 3, 2, I guess. dt. That's kind of how you do it. Maybe you think of this as the derivative is dr dt, but then instead of dr dt, I put the dt on the other side. So cool, that's my dr. My f, well, my f is this vector field. But I've been trying to tell you that I got to put that vector field all into t's. And so, again, it's totally dictated by the curve, the parametrization of the curve. See, what is y when your curve is parameterized like this? Y is, there it is, y is 3t. What's z? Z is 2t. What is x? X is 5t. I need to plug all that in. So here I go. I'm going to do an integral. It's going to go from 0 to 1. My vector field is this vector field, but I'm plugging all the t's in. Here I go. What am I doing? A 3t times a 2t. If you don't mind, that 3t times 2t is 6t squared. Then I have xz, which is a 15t squared. No, xz. Sorry, I screwed that up. xz is 10t squared. Are you guys following me? Mm-hmm. Comma, I need xy. What's xy? 15t squared. 15t squared. I'm doing a dot product with dr. That's what this is, you guys. F dot dr. What is dr? Oh, there it is. 532 dt. Yeah. 532 dt. So that's a lot of, kind of pre-set up work, but now I hope we can execute this, I believe. But that's a lot of, you had to they described the curve. I had to come up with the parameterization for the curve. I had to come up with the 0 to 1 thought. I had to get dr. I had to take this parameterization and change my vector field all into t's. So that's kind of what's involved. A lot of prep work. You got to slice the potatoes before you can cook them. Anyway, here we go. I'm going to do the dot product. The dot product will be a scalar when this is all done. It's going to be kind of easy. It's going to be 30t squared. Plus 30t squared plus 30t squared. That's just a coincidence, I think, you guys. It's not a vector. When you do a dot product, the answer is a scalar. It's not a vector. It's actually 90t squared, I guess, isn't it? I mean, that's what this problem is turned into. Please integrate 90t squared from 0 to 1. Okay. I think that's t cubed divided by 3, t cubed divided by 3, 30t cubed. From 0 to 1, you plug in a 1, we're done. The answer is 30. 30 what? I don't know. There's no units on this. I mean, it's a math problem. It's not really a physics problem. But if this represented some 3D force field, which, by the way, means there's a force field here. There's vectors here. There's, at every point in space, there's a vector. I mean, I don't even know what it looks like, but At every point in space, there's a vector field, and we're on a path traveling through that vector field. And the work done by the vector field on me as I travel through that path from there to there came out to be 30 amount of work.
30 joules?
Yeah, again, there is no units, but if the distance was meters and the force field was newtons, it'd be Newton meters, which can be converted to joules. Work is energy, and work might be foot-pounds or Newton meters, but that can be converted to joules of energy or calories of energy or a unit of energy. But we're math, and in math we're kind of unitless. Anyway, that was one kind of cool example. Again, there's a lot of stuff I can't really see. You know, the fact that it came out positive tells me something. It tells me that the vector field was pretty much with the direction of motion. When your vector field is against the direction of motion, you end up with a negative amount of work. And that's okay. These answers can be positive, these answers can be negative, and they also can be zero. I mean, sometimes maybe the vector field switches halfway, so like half the time it was kind of with me, creating positive work, then half the time it was against me, creating negative work, and the whole result ends up being zero or something. So, or there's this example, you know, what if you're traveling this way, but your vector field looks like this, and it's totally perpendicular? I think there'll be zero work done, because the force field is the force field dot product, the direction of travel. What's the dot product of two perpendicular vectors? I mean, that's what we got here. You know, the derivative of r is like the tangent line of r. So the derivative of r is like this direction of motion. And so we're dot producting little direction vectors with force field vectors. And if they're perpendicular, that's a zero dot product. And so there's different ways that the answer could be zero. It could be positive, could be negative. And it's kind of nice to reflect on the fact that you're either kind of going against the vector field or with the vector field or perpendicular to the vector field or something. But it's hard to see because I'm not making you sketch the vector fields. I mean, the computer can sketch the vector fields. Okay, so anyway, we did it. When I'm in 15.2, okay, we're working on a couple things, but kind of focusing on this guy right here. Now watch me, I'm going to do this generic thing here a second. Let's see. So just generically, the F might be, in 2D, the F might be a vector field, you know, MN, that's what we referred to it as. The R will then be some path, the curve is R, and maybe it's some X, comma, Y. I mean, again, there'll be functions of T, actually. So it'll be some X function of T, some Y function of T. Let me see. And then I want the derivative of this. So I want dr, which is the derivative, which might, if you don't mind, I'm going to call this derivative dx dy. If you don't mind. So really, I don't want to call it a function of T, maybe. Now I'm calling it dx dy. What I'm trying to get to here is this other form. Watch this. So if I'm doing this kind of generically, the vector field might be Mn. The dot product with not r, but dr, which is dx dy. Now when you do this dot product, then you get this. M dx plus n dy. Anyway, this is sort of just an alternative form of this integral. So I don't want you to think this is some new thing I'm teaching you. I tried to show you how, generically speaking, with some vector field mn and some path xy, derivative of that path being dx dy, that this basically is this. And it's just an alternative form. It's called differential form. Let's just try a problem in differential form. There's a batch of problems, 55 through 62. Let me try. I think I want to try 60. So here's the problem. I'm trying number 60. So I'm in 15.2. Trying a little homework with you. So up top, they're saying, please do this integral. This integral is 2x minus y dx plus x plus 3y dy plus x plus 3y dy. And again, this is new, okay? This is in 15.2, but I didn't get to this the other day. So this is new, but what did I just try to tell you? I'm trying to tell you that that thing in that form is this thing in this form, which comes from this. So we're doing one of these work integrals. We're doing one of these, but it's in an alternative form. And by the way, what's the vector field? The vector field is the mn. The vector field is the 2x minus y, comma, x plus 3y. But it's already been dot producted. That's the deal, right? This is a dot product of two things. Go ahead and do that dot product and you get this format. That's the deal. It's already been dot producted, I guess, for me. Okay, now, what's the path? So for number 60, the path says this. They say, let's do this path. The arc on y equals x to the 3/2 from 0, 0 to 4a. They call it the arc on y equals x to the 3/2 from 0, 0 to 4, 8. All right, well, cool. Again, I don't really need a picture of it. What I really need, I think, what I've taught you so far is that I need to parameterize it. I mean, I need x and y in terms of t. I need it parameterized. And again, I can talk like this, or I can talk like this. I hope you don't mind. I'm going to kind of jump back and forth. I can talk a couple of different ways here. It's the same thing, but the fact that the R is kind of out of this, I might talk like this now. I might not bring up R. I might just sort of talk like this. But anyway, how would you parameterize this curve? And maybe you ain't practiced this in a while. This is kind of this is kind of why chapter 15 is cumulative. It makes me recall how to parameterize stuff. It's easy though. Do you got any ideas? The truth is you got a lot of options. Parametric equations are not unique. You could parameterize this a lot of ways. You want to call x cosine t? Then if you do, y will be cosine t to the 3/2. That would be a parameterization. Don't choose that one. That would be stupid. You want to let x be 5t? You could do that. It could be 5t. And then y would be 5t to the 3/2. But that's stupid too. I mean, what would you do? Can we let x be t? Let's do that. That's the smartest thing to do. Let x be t, and then y would be t to the 3/2. And now we got to figure out this. How much t do I need to do what they want? They want me to go from 0, 0 to 4, 8 on this path. Again, I could draw the picture, but it's not real necessary. I said this in the previous lecture. When you let x be t, then t is just x. So if x, let's look over here. If x is going from 0 to 4, then maybe t should go from 0 to 4. I mean, cool. Cool, we're getting there, dude. Here we go. I think that's the parameterization. Oh, you know what I think I need? I mean, I'm ready to throw my x and my y into this problem, but you know what else I need? Like before, I needed the derivative. I needed the dr. Well, I need that also here. It's in the form of a dx and a dy. That's what it is. Right, I need the derivative. So I'm going to just call it dx right here. The derivative of x with respect to t, or I guess it's dx, which would be a 1 dt. What's dy? 3/2 t to the 1/2. I'm doing a little derivative there. 3/2 t to the 1/2 dt. I mean, that's how you do a little derivative like that. If x is t, dx is dt. If y is this, dy is the derivative times dt. That's how we do it. Cool, I'm ready to throw all this in there. Let's do this problem, get rid of this. I need a little room here. I'm going to set up an integral. Here it comes. What's the bounds of the integral? 0 to 4. We figured that out. Everything's going to be in t's when this is all done. Let's see. It's going to be a 2x minus y. So the 2t minus the y, t to the 3/2, all multiplied by dx. What's dx? Oh, just a 1 dt. Plus an x plus a 3y. Okay, an x is a t plus a 3y would be a 3 t to the 3/2. And then it's multiplied by dy. And what's dy? That. 3/2 t to the 1/2 dt. Dun-ta-da! Again, that's kind of it's interesting. It's like I said, like a lot of prep work, a lot of setup work here. And now, then it's doing an integral with it's just a single integral with a single variable. The variable is t, and we just got to knock it out. Listen, I'll help you. Here's one thing I want to say is I think I'll distribute this through here. You know, and then I want to say this. You know, this has a dt on it. This has a dt on it. You know, really I'm going to kind of have a dt out on the end, and I'll have all this junk here to integrate. Is that okay with you? What am I saying? I'm saying I want to take the dt and factor it out on the end, and just add all this crap up if I can. If I can combine like terms, I will. But what do I have here? Well, I got this, 2t minus t to the 3/2, and then I got this. When I start distributing, it's holy shit, it's 3/2 t to the 3/2. That's this first one. And then 9/2 t to the squared, t squared. So that's that. He had a dt on him, he had a dt on him. I factored the dt out the back. Can I combine any like terms? Not much right here though. Here's a couple like terms. Let's combine the like terms before we integrate. That's -1 plus 3/2, -1 plus 3/2. That'll be a positive 1/2 t to the 3/2. This is 9/2 t squared. And here we go. I think I want to integrate from 0 to 4. You know, you do all this prep work, sometimes students forget to do the step called integrate. I mean, you gotta, you know, do the antiderivative, do the integral. So here we go. T squared divided by 2, t squared. When you add 1 to that, that's t to the 5/2. And then you divide by 5/2, or multiply by 2/5. Hang on, so if you multiply by 2/5, the 2's are going to cancel. I think I get 1/5. You guys okay? This 1/2 was out there. Add 1 to that, that's t cubed. T cubed, and then divide by 3. If I divide by 3, it'll kill that 9. It'll leave me with 3/2. Woo! There's the answer. Evaluate from 0 to 4, please. That means plug in a 4. 4 squared is 16. 4, oh my God, this is the square root of 4, which is 2 to the 5th, which is 32. 32/5. Plus, this is 4 cubed, that's 64. 32, this is 3, is 96. Plug in 0, you get a bunch of zeros. Please add these numbers. When you add these numbers, the answer is 118.4.
How did you do that?
I memorize every problem before I come to class.
Yeah, that's exactly.
Good. No, in my head, real quick, I called this a 6.4. That's how I did it. That's a 6.4, and then I added it up. I can't tell you all my math teacher tricks. You might take my job. Anyway, it was an alternative form is how it was presented, but it's still a vector field. It's still this f dot dr in an alternative form. I still felt like I needed to put everything in t's. That's what I've taught you. Everything has to go into t's. I want to tell you something though. I kind of lied. I want you to see something here. And this is, I don't know, I'm worried. I don't want to. Okay, what I'm about to tell you kind of only works, I feel like it only kind of works good when you're in this form. The truth is, you know, if you notice what happened, I let x be t, and then y was t to the 3/2. And what am I trying to say? I'm trying to say, since x was just t, I could have done this in x's. Let me just show you what I mean. I'm going to get rid of all this, except that might have been cool to see. But watch this. I think I could just do this in x's. I mean, if I just do this in x's, this is 2x minus y. But what's y? What is y? X to the 3/2. Okay. Times dx plus, okay, watch this, x plus 3y, but what's y? X to the 3/2. Oh, but now instead of a dy, I need to turn my dy into dx. Now hang on, where are we here? Again, don't look at these t's, because I'm trying to pretend I can do this without the t's, okay? Watch, what is dy? Dy is, based on this right here, dy is the derivative. It is 3/2 x to the 1/2 dx. So that goes here. 3/2 x to the 1/2 dx. Now the truth is, I just erased when we let x be t and we turned the whole thing into t's, you know what we had? We had that same exact problem, except the t's instead of x's. Oh, and by the way, if I'm doing this in x's, what are the bounds for x? 0 to 4. I'm suggesting you distribute and clean all this up, and it's going to look just like this, except you're going to have x's instead of t's. But be careful. I mean, I still think the majority of these problems we turn into t's. But I wanted to show you this. You don't have to always. It depends on the parameterization, I guess, and the equation. So that was 60. You might not be able to do 59 59 maybe you could, but you probably can't do 50. I don't know. Some of these you might not do like that. All right. I'm moving to 15.3. Again. What we're talking about now as we progress through this is we're talking about this integral, which now we just learned has an alternative form. The alternative form is this. Okay? Which is this with the dot product already done, kind of. Okay? Also, though, that's just this in 2D, by the way. You know, if it was 3D, it would have an M and an N and a P, and it would have a dx, a dy, a dz. It'd be more to it. So we're talking about this guy. An alternative form is this guy. And when we move to 15.3, we learn this. We learn this. That if F is a conservative vector field, and we learned about that in 15.1, but if it's a conservative vector field, see now that finally it's going to become important now. If it's a conservative vector field, then this integral that we're working on, the work done by the vector field as it travels this path through the vector field, the work done, this integral is, watch this, is independent of path. That's a huge concept. You know, we do these math problems and we got all these crazy vector fields. You know, in real life, I think you deal with gravitational vector fields. I mean, in real life, that's kind of that's what I'm walking around in right now. I'm walking around in Earth's gravity's vector field. It's pulling me toward the center of the Earth, and I have to fight that every damn day of my life. It's hard work, walking around in this world, fighting that vector field. Also in real life, things move through an electric force field, perhaps, which is similar to a gravitational force field. And one thing about a gravitational force field, watch it, I want to tell you something. There's a little story. So, it turns out that a gravitational force field like that is conservative. It's a conservative vector field, turns out. So watch me. So here I am, I'm here, and I want to go to the library. Now, I'm in this vector field, though, that's Earth's gravity, right? So the vector field is kind of always pointing down, right, toward the center of the Earth. And so here's me, I'm traveling around. Now here's what I'm going to do. First I'm going to go upstairs in building 7 and kind of hang out and kind of get a view of the campus. And then I'm going to climb up the fire escape and go all the way to the top of building 7 and hang out a little bit. And then I'm going to leap off building 7 and fall to Earth. Then I'm going to walk over to the library, but you know, halfway, you know, right under that clock tower, there's a secret tunnel. Did you guys know? And you can go down under the ground, and you can come up, and you can crawl over here. You can come up into the library, and you actually and you end up on the 2nd floor of the library. And then I can walk down the stairs, and I can come here and end up here. How much work did I do? Or that ain't the right question. How much work did the vector field do on me as I traveled this crazy path? And the truth is, I don't know if you studied this in physics yet. The answer is going to be, well, first of all, for any horizontal movement that I did, there was no work. Because that's not me. I'm not fighting gravity, right?
Right. I
mean, I am fighting the friction between my feet and the carpet, but we'll forget that. So as far as gravity, I'm not, so any of this horizontal movement, and so, but you know what? I went up here, so that was some negative work, I think, going against the vector field. Then this was nothing, because it was perpendicular to the vector field. And then there's some more negative work. But then all that negative work just got canceled out when I jumped down here. There's a bunch of positive work that canceled out that negative work. And then all this was nothing. Oh, now here's some positive work, me going down in that secret tunnel. All this is nothing. All this counteracts all that, or this counteracts that. The net result is 0. What was my point? My point was it was independent of path. Okay, what does that mean? That means I could have done this a different way. What could I have done instead? Forget all the damn upstairs jumping and bullshit. I could have just went straight over here. And it would have been the same amount of work. which was 0. Or you know what I could have done? I could have just, maybe I could have screwed, yeah, forget jumping off building 7 and all that. Maybe I could have went over here, went to my secret tunnel, came up here, found that other secret entrance that goes right here, and ended up there. Guess what? Still 0. I mean, it's all independent of path. It doesn't matter what route I would take.
As long as you end up on the same level?
Well, the truth is, the work, right, okay, I'm ending up on the same level, which that's a different scenario in a way. I'm sorry, I kind of mixed ideas here, I'm sorry. Look, ending up on the same level made me have a net work result of 0. The fact that it's independent of path didn't mean I had to end up there, right? So let's just say I ended up here. And then that was 10 feet up in the air. And then, anyway, there would have been some work done. Or actually some negative work, I guess. But all this shit would have been, none of that would have mattered. That would have been this, it would have been the same amount of work as me walking over here and going up 10 feet. And whatever that 10 feet difference. See, it turns out it's like the potential energy. Anyway, I'm not doing a great job explaining this. But I mean, I sort of did, but.
That makes sense.
Yeah. Yeah. All right, let's get back to this. So it's independent of path. If the vector field is conservative, that's the key. So I think before we start doing any of these problems now, I think step 1 will be, hey, let's check and see if the vector field is conservative. Because if it is, I have some advantages perhaps. What I could do is I could choose a new path. You know, maybe they gave me a terrible path and I could choose a new path. Right. So if they're trying to get me to go through a vector field and they say, hey man, do this. You know, this is your path. Good luck. Well, if I find out the vector field's conservative, what could I do instead?
Draw a straight line.
Thank you. I could pick a new path. And maybe that's a smart new path. Right. It sure is a lot easier just to go in a straight line. So maybe I would pick that new path. You know, sometimes I just want to point out, sometimes this is cool to pick this new path. Straight over and then straight up. The problem with that, though, it would involve a C1 and a C2. If you watched my video, we talked about that. You have to do 2 separate problems, C1 and C2. But they might be easier than even doing that straight line. Either one would be better than the crazy curve. So I can pick a new path, and my new path has a lot of options. I could pick a lot of options. Pick a new path. So hang on. So if you're doing one of these, if F is conservative, your options are, well, one option is, okay, watch this. Just do it. Just do it. I mean, so what if it's conservative? Maybe the path they gave you is good. If the path they gave you is good, just do it. But if it sucks, you got this option. Pick a new path. And then there's this third option. Because all that matters, what you just learned here is that all that matters, if it's a conservative vector field, all that matters is where you started and where you stopped. So, the fundamental theorem of line integrals, is that what it's called? Yes. The fundamental theorem of line integrals says that if it's independent of path, you could just do it, or you could pick a new path, or you got this third option. Find the potential function. Now again, this harkens back a few days back to 15.1. But if a vector field was conservative, that means it had a potential function, f of x, y. Go find the potential function and evaluate f of the endpoint minus f of the beginning point. Because what did I just say? If all that matters is where you start and stop, and the path doesn't matter, you don't have to integrate along any of those damn paths. What you can do is go find the potential function, which is a level up above this vector field. You can find the potential function for the conservative vector field, and then just evaluate the potential function from endpoint to beginning point and subtract. So that's, I want to write that as my third option. Find the potential function. Now here's another thought that falls out of that, okay? If all that matters is the end point and the beginning point, and you can do this potential function thing, then what about this problem? You start here, you do this, 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 and you end up back here. How much work was done? If it's in a conservative vector field, you can pick a new path from here to here, which means just chill. You could go find the potential function and evaluate it from the beginning point to the end point, which happen to be the same. So if you do the end point minus the beginning point, what will this be? Zero. Right. So what falls out of these ideas is this idea. And I kind of meant that here, but I didn't do a good job here with that. But I didn't do, yeah. Anyway, I meant a couple things. I had a few things on my mind, but here it is. What we just learned now is that if F is conservative, and C is a closed path, and what the definition of that is, it ends up where it started. It ends up where it started. It's a closed path, like my picture, or just a simpler picture. Sorry for the extravagance there. If F is conservative and C is a closed path, dude, this integral is, can you tell me? The work done, blah, 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 thank you, is 0. Right. So how many of those do you want on your test?
Every single one.
That's right. I don't know if too many make it. They're in the homework. We can work on this, but if it's conservative and it's a closed path, there is no work done, and there's no work to be done on your part. The answer is 0.
This is like distance and displacement, kind of, right?
Yeah.
There's no displacement, so it's 0, but the distance would be the whole line.
Right, and in my story about me wandering around campus, I mean, it would have been right. It would have been a better story if I would have said, I started here, I went down in the tunnel, I climbed up the Eiffel Tower, I took a leap, I did all this stuff, and then I came back, and how much work was done? And because I ended up back where I started, 0. I mean, there was work done. Yeah, maybe the actual phrase should be net. What was the net work done? And not network, but net work. And I think then it would be 0. But there was some positive work done. There was some negative work done. It all added up to 0, though. If you're in a conservative vector field, you got to keep that phrase. I mean, that sometimes we latch onto this idea. Oh, it's a closed path. The answer is 0. Wait a minute. Is the vector field conservative? I mean, that's right. That's the key to all these options. I mean, that's what happens in 15.3. If the vector field's conservative, dude, we got options. And if it's a closed path, you wouldn't do any of these. Again, if it's a closed path, you just say the answer is 0. You don't do any of these. So if it's not a closed path, then you got more options. If it's not, you pick a new path, or you go do this. This is good stuff. I want to do a problem or two. And I don't know if I'm going to get into 15.4. 15.4 is the last cool idea, but it's a little unrelated to this. I might have to wait till Monday. Let's stick with this and do a problem. If I go to 15.3 and pick a homework problem, it would be I want to do 16. So here. So 60. They give me a vector field. They present this in 2x minus 3y plus 1. They give me this alternative format here, kind of 2x minus 3y plus 1 dx plus, minus 3x plus y minus 5 minus 3x plus y minus 5 dy. So here I am. Now, can you tell what f is? You see it, don't you? You're not going to make, well, I was going to say, you're not going to make me write it, are you? But here I am. I just want to make sure you're clear. There's f staring right at you. It's in this alternative form. Listen, see that negative sign? That's part of it, isn't it?
Yeah.
So that's negative 3x plus y minus 5. Okay. Oops. Right, there's my vector field. I mean, it's right there. I don't know why I wrote it again. Except, I think before I do any work, I want to see if it's conservative or not. I mean, that's what I want to do because that gives me some options. So, how do you check if a 2D vector field is conservative? That was in 15.1. What we would do is we would do dm dy, and we would check to see if it's dn dx. And if that's if they were the same, then it's conservative. So what is, and this is m, and this is n, so here we go, what is dm dy? Dm dy, the partial derivative of this with respect to y? Negative 3. What is dn dx? The partial derivative with respect to x? 3. It is a 3, but there is a negative sign there, so it is a negative 3. If you would have forgot that negative sign, you would have been in trouble, though. Right. It is negative 3. So, awesome. So, yes, f is conservative. Okay, cool. F is conservative. I got these 3 problems. I got 4 problems here in 16. I got an A, B, C, and a D. Let's see, what's A? A is, okay, A is this. Holy shit. A is, I got to go from this triangle. Oh my God, that's a C1, and then I got to do a C2, and then I got to do a C3. I mean, that's how you got to do it, you guys. You got to break it into, you got to do 3 different integrals, 3 different parameterizations. It's actually going this way. I mean, this is going to suck. Unless you've got some advice for me.
Looks like it's closed loop. Yeah.
Oh, thank you. I'm in a conservative vector field. This happens to be a closed path. It starts and stops where, I don't have to do anything. The answer to A is 0. Thank you. And F is conservative. I maybe I better say that. I mean, this is just me explaining why the answer is 0. Right. Cool. Cool. Closed path. What about B? B kind of sucks. Let's see. B is, okay, they do a good job. They point to this and they call it x equals the square root of 1 minus y squared. I'm, real familiar with these equations and stuff. It's a semicircle, you guys, and you've worked with this stuff too. This is a circle of radius 1, and if you solve for x, it's the right half of a circle of radius 1. It's the right half. It's the positive square root. So it's the right half of a circle of radius 1. Anyway, it looks like they want me to go from here to here. The orientation is important. This point is -1, 0. This point is 1, 0. No, that's not right. I said that backwards. 0, -1 is what this is, of course. 0, 1. Anyway, that's what I'm doing. Okay, well, I am in a conservative vector field. So I got my options. Do you want to do that path? You could just do that path. There's nothing wrong with doing that path. Or you can pick a new path. Or you can go find the potential function and forget the damn path. The potential function is evaluate the potential function from the end to the beginning. Or from the beginning and the, right. I think I'll pick a new path. What path would you pick?
Straight down.
Well, don't forget you're going up. But straight, so go straight up. From here to here? He wants to pick this path. All right, let's pick that path. Now, can you parameterize that path? X is something, Y is something. I'm trying to make a parameterization for that path.
X is t and y is square root of 1 minus t.
Good guess. But not... Let's see. Here's what I always tell myself, talk to myself. I say, who's moving? Who's varying?
Y.
Y. So let's let Y be t.
Right.
Yeah. Y is going to be t. And X is kind of stuck. Where is X stuck? At 0, right. It's X equals 0 is what it is. Right. Now, again, same thing over here. If I was over here at X equals 8, and I was doing this at X equals 8, then I would still let Y be t, but this time X is 8. I mean, if I was over here doing, but anyway, sorry. Right. X is a 0, I think. X is stuck on 0. Y gets to vary. And what do you think? What t values would be good to complete this path?
-1 to 1.
Exactly. I mean, if y is t, then whatever y's bounds are, those are t bounds because they're equal to each other. So I think y wants to go from -1 to 1. So I think t should go from -1 to 1. Yeah. I write it like that. But anyway, good. We're doing pretty good. We're setting this up. We're picking a new path. We're going to do, what are we doing? This integral? We're doing this integral. I guess that means I need a dx and a dy, right? I got my x and my y. I got my bounds. I need a dx and a dy. What would you call dx? The derivative of x? 0. What would you call dy? 1 dt, kind of. 1 dt. Okay, here we go. Then we're doing this integral. Here we go. It's this integral. I think the bounds are -1 to 1. We're turning everything into t's. Hey, remember last time I said on a problem like this, maybe we could leave it in x's or leave it in y's. You know, with this path, I don't think you can. I don't think there's a way to... I mean, with this path, we need t's. We need parameterization to make this path. I don't have a... I don't know, maybe I could. I mean, y is just t, x is just 0. I don't know. I like it. I don't know. I'm used to thinking in t's. I'm doing this in t's. Hey, it's kind of nice. Watch this. The dx is a 0. So that makes this whole thing 0. You with me?
Mm-hmm.
So I'm not going to fill any of that in. That's a big fat 0. What's coming over here? A 3x. Well, that's a 0. A y. Okay, y is a t. And then a -5. And then dy. What's dy? dt. Dude, this is easy. I'm going to distribute that negative sign. What's going on here? This is a -t plus a 5. And I'm integrating with respect to t. From -1 to 1. I mean, it turned out to be easy. Okay, I'll finish it with you. -t squared over 2 is how you integrate that. -t plus 5t plus 5t. From -1 to 1, you plug in your 1. This gets kind of weird here. Let's see. It's -1/2 plus 5 minus, when you plug in your -1, it's -1/2 minus 5. Hold on. I am subtracting. -1/2 minus -1/2, they're going to cancel. 5 minus -5, they're going to add together. The answer is 10. Excuse me. Part B. The answer is 10. 10. That's a 10.
Would option 3 always be, does that always work?
That's a good question. There might be times when some of these aren't better. It's hard for me to say what's better. That was pretty easy. That was an easy path, right?
Yeah.
If the new path can be an easy path, then that's cool. But we probably could have done option 3. I just didn't. Let's keep talking. I got a few more minutes, and I want to, because Anyway, because this problem 16 has a couple more. It's got, here it comes. Here comes a C and a D. Here comes C. Check out C. Check out C. I'm gonna, I don't know, I like my notes. I guess I'll get rid of A here. I'll get rid of B. All right, I'm gonna work on C. So here's C. C is this path. Same vector field, by the way, but we're doing a new path. 0, 1 to 2e squared. We're on this curve. Wow. Okay, so we're going from here, which is the point 0, 1, to this point, which is the point 2e squared. And we're on this path, which is y equals e to the x. All right, cool. And so here I go. What am I doing? I want to do this integral. It's this integral I'm doing, you guys. I'm doing this integral, but we already checked. The vector field is conservative, so I have options. Do you want to do that path?
Not really.
Not really? Okay, then you can pick a new path. I want to say something. You know, when some people, you might say, oh, I don't want to do that path, I want to pick a new path. And then you might think to pick this straight line path. Like we think straight lines are so good. But straight lines aren't always that good. In fact, what would be the slope of this line? It would be, I mean, I have to find the equation of this line, and the slope would kind of suck. It'd be change in y, e squared minus 1 over 2. The slope would be, yeah, I mean, I could decimalize it, but straight lines aren't always that great. And then so here's a suggestion. This is not a bad path because x gets to be 0, right? And then if you go straight over, that would be kind of nice. That would be y equals 2, I guess. But it's kind of nice to do that, but then that creates two integrals. You got to do two separate integrals for those two separate paths. But sometimes that's a good option. Look, I think I don't want to just do it, and I don't want to pick a new path. On this one, I think let's try this option, okay? All right, so that means I need the potential function. Now, that was practiced in 15.1. Let me remind you how to do that. The potential function comes from the conservative vector field. The idea was, if I have a potential function and took its gradient, it would be the vector field. So hold on a second. If you have a potential function, hang on. If you have a potential function and you take its gradient is the partial derivative with respect to x. If that's this, then this is, I know it's called m, but if it's conservative, then this is fx for some f. And this is fy for some potential function f. And to get from fx back to f, what do? To get from, you integrate. And you integrate with respect to x. So here, this is how you get f. You integrate this dude with respect to x. Also, you'll integrate this dude with respect to y. Don't forget that negative sign. We'll integrate this dude with respect to y. And together we'll find an f. We'll find the potential function f. All right, here we go. Integrating with respect to x. I think that's x squared over 2 kills the 2. Integrating with respect to x. I think that's a negative 3xy. Integrating with respect to x. I think that's a plus x. Plus some constant. But when you're integrating with respect to x, who did you just treat like a constant? Y. So this plus c on the end of these could be a function of y. So this is my f. But what I have to do is kind of look at it and try to match it up with this f. Let's calculate this f. This f. All right, so I'm integrating this with respect to y. I'm integrating, there's a negative. As I integrate, I'm going to distribute the negative sign. So integrating a 3x with respect to y is 3xy. With respect to y with a negative sign in front. What's this? A y squared over 2? A y squared over 2 with a negative sign in front. With respect to y, what's that? A 5y? But it'll be positive. I'll distribute the negative sign, it'll be a 5y. Plus some constant, which could be a function of x's. Now you take this f, and you take this f, and you sort of match them up and build your ultimate f. Your ultimate f, or your final version of f, just comes from matching up what these guys have in common. What do they have in common? Oh, well, they both got this negative 3xy. All right, so that needs to be in here. What else do they have in common? Well, I don't know, dude. Look, this has an x squared plus x. This one doesn't. Or does it? Right? All those x's match up with this thing, which is some possible function of x. Yeah. So that matches that. That needs to be over here. X squared plus x. Okay, what about this crap? This doesn't match anything in the other dude. This doesn't match anything at all up here. Or does it? It's that. So that needs to be in here. Plus some possible actual constant k. So that's it, you guys. That takes a little work to find the potential function. It really isn't that bad. I drug it out with a lot of my explanations. But we found the potential function. Do you know how to finish this problem? You find the potential function and you evaluate it. You do f of the end point. What was the end point? 2e squared minus f of the beginning point, 0, 1. You plug this point in, minus plug this point in, and that's the answer. I could do that. I mean, I'm running out of time.